Good morning, everyone. Good morning to everyone who's tuning in on this Sunday morning, a snowy Sunday morning today. Just looked out the window. Very exciting. I'll go for a walk with my daughter and my wife later. It's my wife's birthday tomorrow, so she'll enjoy that. Yes, today's session is about particle physics. And I know that particle physics doesn't really feature on... good morning, Lex. Now, I know particle physics doesn't really feature on GCSEs, but it does feature on A-levels, and Year 11's about this time and trying to make difficult decisions about what A-levels they want to study, and Year 10s will have to make that decision at some point in the near future, so I didn't think there was anything wrong with including this session. The physics tends to be a sort of, they call it a spiral curriculum. So the same topics keep coming up. Good morning, Jackson, and good morning, Ted. Yep, the same topics keep coming up over and over again, just at different levels of complexity. So what's quite nice about particle physics is, if you're GCSE, actually you won't have met this before. This is one of those topics that just appears in A-level, and often it's taught right at the beginning of A-level because of the fact it's new. So it entices students and they think, oh, this is new, this is exciting, and gives them something a little bit different to start their A-levels with. And what's quite nice about the particle physics at A-level is it's not actually too challenging. So I recorded that series of videos, 12, I think it was 12, I can't remember now, I think it was 12 videos all about particle physics. And the link to them is below. If you haven't watched them yet, don't worry. It's helpful to have watched them before, but it's about an hour and 50 minutes worth of video, so you haven't got time now. But you can watch it again later if you haven't watched it yet. And those are going to give you the background for today. Good morning, Tilly. Today's session is going to be about answering questions at the sort of level of difficulty that come up at A-level. And you'll see that it's very accessible. So there's a bit of problem solving, a little bit of number crunching. Don't really need calculators for this. A little bit of number crunching, but it's more, these are logic puzzles. And that's good for students of any age to work through these sorts of puzzles. Now, I am going to remind anyone who doesn't know this, or anyone that's tuning in for the first time, or anyone that might have forgotten, that we've been trying out something new in these sessions using Spiral to get answers off people, rather than people chucking the answer into the chat thing here, which can get lost and there's too much for me to see. Having Spiral and chucking your answer into there means that I can see answers appearing at different times, but you lot can't see the answers appearing at different times, so you don't feel rushed or stressed when other people are getting the answer right and perhaps you're not. It keeps a small amount of anonymity in your answer, which might help people open up and try things a bit more. If, when you're looking at a question, you just don't know the answer, just give it a go. And if you really have so absolutely wanderingly in the lost, you don't know what you're doing, well, let me know. You can either type it into the chat if you're happy to do so, or put it onto Spiral, and I can see that you're struggling, and we can maybe go through some of those areas. So let's get cracking with it. Introduction to particle physics. And today I'm using emojis for some reason. Just because I'm running out of ideas for silly little pictures. It's not my forte, putting silly little pictures on PowerPoint presentations. Okay, so a brief bit of background for anyone who hasn't looked through those that series of 12 particle physics videos. These are the particles that we're going to be looking at today and that you'll be looking at in your A-level if you choose to study it, and I really hope that you consider it. It's a really good A-level. It gets called the particle zoo. Mainly that's a historical term because of how confusing it got in the history of particle physics when all of a sudden we started creating all these new particles and we had to figure out the relationships between them and cataloguing different particles and sorting them into groups. It was very similar to how in biology you catalogue different animals and plants, and I don't know, I'm not a biologist, but you assign them into little groups by their characteristics, and it was the same sort of process. So this gets called the particle zoo. And these are all the particles that we're going to talk about, but we're going to sort it into 4 categories of particles. And I've just color-coded them here. The category on the left here, all of those are what we call baryons. And for today, what you're going to need to know, don't worry too much about the word baryon if you're not sure what that means. It's a new term. You've never heard it before. Basically, a baryon has 3 quarks. or quarks if you prefer, which I don't. 3 quarks. So there are 3 quarks in each of these particles here. They're what we call constituent particles. I think that's what we call them. They contain other particles. Baryons have a special number called baryon number, which is 1. And everything outside here has a baryon number of 0. So these are just numbers. If you ask what's the baryon number of a kaon, the answer is 0. What's the baryon number of a, this is the Greek letter lambda, 0 particle? Well, it's 1 because it's a baryon. Now, over here we've got the yellow particles. These are called mesons. Mesons contain, they're constituent particles. They contain a quark and an antiquark stuck together, a quark and an antiquark. And so when you look at all these particles, pi, kaon, this thing here, which is eta, those particles all contain quarks and antiquarks. Well, 1 quark and 1 antiquark. They're not baryons, so the baryon number is 0. And then we've got this little group in here, which are called the gauge bosons. They're the ones that bounce backwards and forwards to produce forces. And there are others, but these are the ones we're concerned about for now. And then we've got these particles in this pink box here, and they are the leptons. So if you're at home and you've never heard these terms before, you're thinking, whoa, you've just given me 4 complicated terms plus some things called baryon numbers, and that's an awful lot to remember. Well, it is. If you want, take a screenshot of this and maybe have it open in the background if you need to go back and refer to it. Maybe make a little note that these blue ones are called baryons, these yellow ones are called mesons, and these pink ones are called leptons. But when it comes to memorizing things, that's almost it. There's not that much more to memorize for this topic. Now, it would be lovely if we could have a nice system where capital letters were baryons and lowercase letters were mesons and things, but we don't have that. I'm afraid we don't. But there are only 3 letters that would be mesons: pi, k, and this special one called eta. So eta, pi, and k are mesons. Then if you look at the leptons, there are only 2 well, there's 3 leptons. There's E for electron and positron, mu for muons, and then these things, it's not a V, it's the Greek letter nu, N-U, Greek letter nu, and that's it. So 1, 2, 3 different particles that make up leptons, 3 different particles that make up mesons. Everything else is a baryon. So that's the starting point. The next thing is, the charge of the particle is indicated by the symbol in the top right. So you can see this thing here has 2 plus charge. This thing here has 1 plus charge. This has 0 charge. It's neutral. This thing here has minus charge, 1 negative charge. So charge is easy to spot. The only other quantum number you're going to be interested in at the moment is this thing called strangeness, which is a weird idea, a weird quantity, strangeness. These first particles here, a proton, neutron, delta particles, these have no, strange. These particles have no strangeness. Sigma, S for sigma, S for strange, they are strange. But they've got a strangeness of, in all 3 of these cases, -1. Whatever that means. This thing here, lambda, has a strangeness of -1 as well. Then these 2, the Xi particles, have a strangeness of -2, and omega has a strangeness of -3. Usually we'd spend 3 weeks going through this, and I'm trying to cram it into 10 minutes so we can do some questions. So if you're lost, I get it. There's a table coming up that's going to help. Practice will make perfect. Here we've got some pions. Pions aren't strange, but kaons are strange. And with kaons, the strangeness follows the charge. So K plus has a strangeness of +1, K minus has a strangeness of -1. And then K0 has a strangeness of +1, and K0 bar, which is an anti-K0, that has a strangeness of -1. Eta's not strange. Nothing else on this table is strange. So all right, that's a lot to digest. I'm going to make it a little bit worse now because I'm going to throw some quarks at you. On the left here, we've got 3 quarks you need to remember. And maybe, again, take a screenshot of this if it's helpful. Or maybe make a quick note of it. But when we go through the quarks, exactly, or quarks if you prefer, but these are the 3 quarks that we're going to look at today. They're the quarks that A-level gets restricted to. There are 6 quarks and 6 anti-quarks, but we're just going to look at these 3 quarks for today. So charge-wise, that's what the Q means. This has a charge of 2/3 of the elementary charge. Down quark has a charge of -1/3 elementary charge. And the down quark and the strange quark are almost the same, except the strange quark has much more mass. And so we say, oh, that's strange. And so we call it a strange quark. It's strange. It has a strangeness of -1. It's historical, the reason why we give it a strangeness of -1, but it's stuck. So strangeness of -1. These things over here in blue, they're your leptons with your electron and your muon leptons there. So the logic puzzle is trying to figure out, this is what we're going to start with, trying to figure out what quarks make up the baryons or mesons that you're asked about. And I'm going to start with a grid. Now this is from one of my various question generators, which you've got access to via the Facebook group if you're on it. If you're a regular participant, then you can join that Facebook group. There's a link to it in the description of this video. But you can see over there we've got a list of particle names. Proton, positive pion, delta plus, lambda 0, delta minus, eta 0, a sigma. Try one more time. What am I saying? Sigma. An omega minus, a neutron, negative kaon, and a delta plus plus. And the first task, the first challenge, is to figure out what the quantum numbers are for each of these particles. Once you know those quantum numbers, then it's figuring out the quark composition. That's going to be the challenge. So let's start with the quantum numbers. And we'll just start easy with the proton. If you get this wrong and you don't know, it's okay, because as we go through it, you'll start seeing the patterns and it will become intuitive. But you've got to try and get it wrong to learn how to do it. So let's start with the proton. What I want you to do into Spiral is type what the baryon number, charge, and strangeness is for a proton. If you don't know, just guess. The numbers are going to be something from -1 to +1, although if it's charged, it could be +2. Strangeness, I suppose it could go all the way up to -3. But just try. Just throw some numbers at me. So B equals something. Q we usually use for charge. But if you use a C, I'll understand what you mean. Equals something. And then S equals something. So chuck your answer into Spiral and we'll see what you've come up with. Well, this is looking very promising. See, Jack has skipped to the next step. He's even given me the quark composition. We're coming to that in a second. Certain particles, it's worth remembering the quark composition. This is one of them. So we're talking about a proton. You've got to ask yourself, is a proton strange or not? Is a proton strange? Does it have this property where it's strange? Strange quarks will decay into down quarks. They're a bit more energetic. They're a bit more... Actually, they won't. They'll decay into up quarks. They could decay into down quarks via the Z0 boson. I've gone too far. Strange quarks will decay into up quarks. Strangeness decays away. The mass will reduce for the particle, dissipating energy. So protons, they're the end of the line. They're the last particle on the decay chain for baryons. Let's have a look at some of the answers here. Okay, a few answers definitely coming through. So, for baryon number, it's going to be 1 if it's a baryon, 0 if it's not a baryon, and -1 if it's an anti-baryon. Those are the three options. They're the only three options. So baryon number can't be 5. It's only going to be 1, 0, or -1. I'm afraid protons are not strange. They are very low energy particles, so they don't have any strangeness. Baryon number of 1, they are baryons. Charge is 1, because there's one little plus in the corner, but they don't have any strangeness. They're not strange. So now, if you could let me know what you think the quark composition is. That means we're going to use this table here, and knowledge of the fact that it doesn't contain any strange quarks. It's a baryon, so it has 3 quarks in total, and the charge has to add up to +1. So what would the quark composition be for a particle with a charge of 1? So what I want you to do is list the quarks. Do you think it's 3 up quarks? Do you think it's 2 up quarks and a down quark? Do you think it's 1 up quark and 2 down quarks? Do you think it's 3 down quarks? Do you think that perhaps it's an up and a strange quark? Or, you know, what do you think the composition is? How can I combine those numbers, -1/3 and 2/3, to get +1? And I've got to have 3 particles. I've got to have 3 quarks. It's a logic puzzle. It really does, Aaron D, because you've got it there. But my advice will always be not to use it. My advice will be to practice until you don't need it. Because these questions you can answer so quickly when you've got it. Something clicks, something, the penny drops, and all of a sudden, all of this becomes almost trivial. You just see the question and go, oh, I know that. It's a such and such a quark composition. And you won't have to think about it. Plenty of answers are coming in at the moment. Yep, good. Okay, so we've got anyone that's tuning in a little bit late, please do join the Spiral group. There's the link for it. Do join in with the questions. As I'm asking questions, you can chuck your answer in there. No, Wombat, a delta particle does not have any strangeness. So a delta particle only has up and down quarks in it. If a particle has some strangeness, then it has either a strange quark or an anti-strange. Sorry, strange quark or a strange anti-quark in it. Okay, so moving on to the pi plus. What are the 3 quantum numbers for the pi plus? After we go through this table slowly, we'll speed up on the next few tables. What's the properties of a pi plus, the quantum numbers? Good. 2 answers have come through so far, both of which are correct. Oh, Aaron's given me the quark composition as well. Okay. I was just going for the numbers first. Once we've got the numbers right, we can check the quarks. You don't have to wait. If you can work through all of these, and then as we go through them, you can chuck your answers in. You don't have to wait for me to go through the answer for one before you move on to the next one. So, pi on plus. That's right. Yep, good stuff. Good stuff. It looks like we've got this one. So Antonio, just check your quark composition. We're going to look at the quark composition now as 1, 2, 3, 4. A few people haven't yet popped an answer in. You don't work it out, Ted. You have to remember it. But there aren't that many particles that are strange. So strange particles are your sigma particles. They've got a strangeness of -1. Lambda particles, strangeness of -1. Xi particles, strangeness of -2. Omega particles, strangeness of -3. Your kaons have a strangeness, and it depends on what the charge is. Just waiting for a few more answers to come in before we go to the quark composition. 1, 2, 3, 4. 4 people who are on Spiral haven't answered yet. Oops. There we go. Okay, well, I'm going to have a look at the... let's have a look. 0, 1, 0. That's the pion. It's not a baryon, it's a meson. Has a charge of +1, we can see that one, but it has no strangeness. So what's the quark composition going to be for this particle? If it's a meson, that means it contains 1 quark and 1 antiquark. Baryons contain 3 quarks. Yeah, so Arandeep, the reason why I've included all of these is because there are questions on past papers that have asked about them. Yes, possibly Wombat. Arandeep, what you wouldn't be asked is to remember them. Not necessarily. You wouldn't see a Xi particle and think, oh, crumbs, what's the strangeness of that? It would be the other way around. It'll say, what's this mystery particle? You'd work it out, what the properties of this mystery particle are. You wouldn't necessarily have to know the name of it, but because it's possible to have that mystery particle as part of the question, I've included it, and there's no way I can include a mystery particle without including its name. So that's why you've got things like Xi particles coming up there, Arandeep, okay? So it's going to have a quark and an antiquark. So any answers that have 3 quarks, I'm sending back. It is a meson. That means it's got a quark and an antiquark. Marked one correct that's not correct. So we have to add together a quark and an antiquark. Now, an antiquark is a particle. If you look at the quark list here, all you do is you reverse both of the quantum numbers. So, or in this case, the quantum number. So the charge for an up antiquark is -2/3 e. The charge for an anti-down quark, a down antiquark, is +1/3 e. That's the charge of a down antiquark. So you just reverse the numbers. Let's go back to the question. So the quark composition for pi plus. Okay, so the up quark has a charge of +2/3. But I've got to have an antiquark now, because I've got a meson, which means it's a quark and an antiquark. So +2/3, and then the down quark has -1/3. So an anti-down quark, which we indicate by putting a bar over the top, an anti-down quark has +1/3. So the opposite of -1/3. So +2/3 for the up quark, plus +1/3 for the anti-down gives us +1, which is the charge we needed. Yeah, not easy. So up anti-down would be the correct answer. So now we're going to move on to the next one. Could I have the quantum numbers, please? If you want me to work through any of them, written out in full, I'm happy to do so. Got my whiteboard ready to write anything. All you got to do is ask. I'm here for you. Quark composition of a delta plus. Delta pluses are on your A level. Two answers so far, both of which are correct. One of whom has even given me the quark composition already. Oh, two of them have given me the quark composition already. No, I'm after the quantum numbers at the moment. Aaron, if I get the quantum numbers, then we can move on. And this table, we're just going through a bit more slowly. Then the next table, we're going to rattle through much more quickly. Yep. Well done, Ted. Well done, Lex. Well done, Aaron. There's three sets of types of questions I want to do today. One is this, figuring out the quark composition. That's a very important skill. One of them is a decay possible? Is an interaction possible? So looking at conservation rules, and we'll have a look at that one next. And the last one is interaction diagrams, filling in the gaps on interaction diagrams. And those are the three sorts of questions you can get on this topic. Okay, so I keep sending an answer back for the same reason. A delta plus is a baryon. Delta plus is a baryon. So that means it has a baryon number of 1. Yes, it could, Wombat, absolutely. And that you'll find as a possible quark composition of a 𝗫0. Also, because it's going to have strange and anti-strange, it's going to be a little bit more massive. So it could be an 𝗃0. 𝗃0 and 𝗫0 can have the same quark composition, but 𝗃0 is more energetic. So everyone got the charge, and I think most of you got the strangeness. Baryon number was tripping some people up. So delta particles are generation 1. They contain just quarks and just quarks. They contain 3 quarks because they're baryons. So looking at the table, the last one's probably going to be pretty trivial, and I'm going to give you the answer to this one for the quark composition. It's got the same properties as a proton, and it contains the same quarks as a proton. So why is it a different particle? Well, the answer is it's more energetic. You know, one of those quarks, I don't know, maybe 2 of those quarks, one of those quarks is in an excited energy level. It's more energetic. So it could decay a delta plus, it could decay into a proton if energy is emitted in that decay. In the same way as an excited atom can decay into a ground state atom by emitting a photon. When the electron drops from a higher energy level to a lower energy level, it's the same thing. An atom is a composite particle. So is a delta plus. It's just a baryon. It's a smaller composite particle. Okay, so lambda. Lambda's a tricky one, which you might not know what it is yet, but you can figure out the charge on it. And you know whether it's a baryon or not, maybe. So we'll see how you get on. Allow yourself to make mistakes, because that is how you'll learn. Oh, I haven't clicked go yet. There we go. Yep, so remember with baryons, the strangeness can either be 0, or it could be -1, or it could be -2, or it could even be -3. You can't get a strangeness of positive with a baryon. You can get a positive strangeness with an anti-baryon, which contains 3 antiquarks, but not with a baryon. Some people, it feels a bit like you're just shouting out random numbers at the moment. Ted, I'm giving you a tick for the first part of your answer, but not for the next part. That is correct. Well done. Oh, you can't see what I'm pointing at. Good. Okay, so most people are still joining in. Some people have stopped joining in now, which is a real shame. Keep trying. There's some sort of analogy somewhere about sportsmen having to get things wrong loads of times before they get things right, but I'm not a sportsman, so I don't know that analogy. Yeah. So it is a strange particle. It's a second generation composite particle. It's a strange particle. So it's a baryon, so it's got a strangeness of -1. Contains 3 quarks. If you recall, if it's it contains a strange quark, that's a strangeness of -1, not +1. No charge. We can see that from the symbol. So the quark composition of a particle with 3 quarks with a strangeness of -1, therefore one of those quarks is a is a strange quark, therefore it's got a charge of -1/3. So what do I have to add to -1/3 to get it back to 0? Pink Dolphin, you learn it. You go back to the first table and you have a look. Protons and delta particles have no strangeness. Sigma particles and lambda particles have strangeness of -1. Xi particles have a strangeness of -2. And omega particles have a strangeness of -3. So the quark composition of this is up-down strange. Right, let's do delta minus. Let's do delta minus. Go ahead and give me the quark composition as well as the quantum numbers, if you like. I'll try and speed up a teeny bit. As these start filling in, you'll be able to refer back to previous particles and see if there are any patterns. Yep. So clearly a few of you have mastered this. What's quite nice is that some of those who are getting these answers right somewhat consistently, some of you who are getting it right somewhat consistently are doing GCSEs. So if I've given you a correct star and you are and you haven't put your quark composition, feel free to take your answer back, edit it, figure out what the quark composition is, then chuck it back at me. Remember, your quarks are an up with +2/3 or a down with -1/3. I haven't included them on the table, you can see, because I want you to try to learn them. Ah, right. Freya, I'm giving you a correct answer for the first part, but the quark composition isn't correct. Okay, so it's a baryon. We know it's a baryon. It's a delta particle is a baryon. We know it's got a charge of -1. And we know that because it's a delta particle, it's got a strangeness of 0. That means we've only got down quarks and up quarks to play with. There's no strangeness, so it's down quarks and up quarks. It's a baryon, therefore it has 3 quarks. So what 3 quarks can I combine to get a charge of -1? Minus a third plus minus a third plus minus a third is -1. Okay, I'm going to give you the properties of the eta particle. What's the quark composition? Okay. Giving you the properties. There are 3 possible correct answers here. I'll accept any of them. Any of the 3 correct answers. Right now what I'm doing is ticking them as they come through. It's a baryon number of 0. That means it's a meson, which means it contains a quark and an antiquark. It's got no strangeness, so I need to combine a quark and an antiquark to get a charge of 0. Now, with this answer, some people will say, well, how is that possible? Because your particles are going to annihilate. The answer is yes, they do. Eventually, there is an interaction between them, eventually. But they're in this metastable state. The lifetime is slightly longer. James, I'm going to interpret your -d as an anti-d and mark it as correct. You'd usually put the bar over the top, but it's not easy to do that with the tools we're using here. Yep, good. Okay, lots of correct answers there. So down anti-down or up anti-up, strange anti-strange. I'm going to give you the properties of the omega particle. What's the quark composition got to be? This is particle physics. If you want to pop the answers into Spiral, the link to it is there. I'll just put it into the chat. And then I can check as you go along. This is some of the earliest stuff that you'll do at the beginning of A-level. But it's a logic puzzle, which means it's good for GCSE students to cut their teeth on a little bit. Yeah, okay, correct answers are coming through left, right, and centre for this. It's got a strangeness of -3, and the quark with a strangeness of -1 is a strange quark, so you've got to contain 3 strange quarks. It's the only possible answer. Yeah, people are giving me that. That's good. Okay, neutron. Quark composition of a neutron. Go. Yeah, the particle physics comes up in AS level as well. Yeah. Not at GCSE level, but I think you can see that it's okay. It's not a difficult topic once you get over the learning a few particles. There aren't that many particles to learn, and I think that seems to be the barrier here. We haven't got time to sit there and memorize those particles now. But once you've got the particles, can you see how quickly the answers are just pouring in and they're all correct? for these particle compositions. Up, down, down. So a kaon is a meson, doesn't have a baryon number. Well, it does. Its baryon number 0. It's got -1 charge and -1 strangeness. So what is the quark composition of the negative kaon? Yeah. Right now what we're doing is combining 3 quarks from this list for a baryon, or a quark and an antiquark from this list for a meson. Antiquarks have these quantum numbers reversed. Obviously mass you don't reverse, but the quantum numbers here get reversed for antiparticles. So we are just adding together 3 particles, or a particle and an antiparticle, to try to figure out what the composite particle is made out of. So the K- meson has no baryon number, charge of -1, strangeness of -1. So we've got to figure out what the quark composition is for that particle. How do I combine those quantum numbers for a particle and an antiparticle to get a K-? You get given a lot of this, but if you learn it, you will do far better. You won't have to look things up. It's much quicker when you can learn it. I'm going to send an answer back because you've given me 2 quarks, and it has to be a quark and an antiquark. So 1, 2, 3, 4, 5, 6, 7 people have given me the correct answer there. Oh, there we are, another one. Yep, so strange anti-up. Strangeness of -1, so we know it's got a strange quark. So how do I make the charge down to -1, where my strange quark has a charge of -1/3? Well, I need a charge of -2/3, which is an anti-up. Quark and an antiquark is a meson. That's what a delta ++ is. What quarks does it contain? Brilliant. Absolutely brilliant. Yeah, it looks like once you know what the once you know what the quantum numbers are, you're very good as in general at finding what the quark composition is. The answers just come in very, very quickly. It's that initial step of learning those particles. Now, the nice thing is, the more you do this drill, which is available to regular participants, let's go to the Facebook group. The link is in the description below. You can download this drill that we're using here, and you will learn these through repetition. Up, up, up. You'll learn this through repetition. Now, I'm going to move on, actually. I've got loads more here, you can see. Not really, Wombat. No, what these are, when you write a quark composition, you are writing a wave function multiplied by a wave function multiplied by a wave function. So it's a superposition of 3 wave functions. It doesn't matter what order you do those in. That's beyond A level. But that's what the letters are. Right now you just think, oh, U is an up quark. Actually, there's some physical meaning to that. It's a probability distribution function for an up quark. It's such an exciting subject. But look, I'm gonna just go ahead and give you this table. If you want to watch it back, you can always pause it at each point where I'm stopping, and then you can check your answer yourself. Oops. You can sort of, or maybe cover up part of the screen where the answers appear. Because I want to get on to the conservation rules now, and I've got loads of these questions. I mean, my question generator generates questions ad nauseum, and there's a switch so you can make it include anti-baryons as well. But once you've figured out the pattern for the quantum numbers, then the quark composition, I went on a bit, didn't I? The quark composition is almost trivial. It's just adding up thirds and 2/3 in the right order, in the right amount. Some of this will be repeated, of course, because these are randomly generated. Okay, let's move on then. So, New part to this. This is the second skill for particle physics. Is a decay possible? So you know what these quantum numbers are. Here I've just split something called lepton number into two families, electron lepton number and muon lepton number. Electron leptons are indicated with an E or a subscript E. Muon leptons have a mu or a subscript mu. And just remember, electrons and muons have negative charge and a lepton number of +1. They are matter. Whereas positrons and anti-muons have a positive charge, but they are antimatter. That's the trick. B for baryon number, S for strangeness. This decay is possible because when you add up the quantum numbers on one side of the equal sign to the other, they balance. This one's not possible because the leptons are wrong. On the right-hand side, we've got a lepton. We've split the electron into the electron. Sorry, we've split the lepton number into electron lepton number and muon lepton number here, Freya. So electron lepton here of 1, an electron. Sorry, electron neutrino, there we go, here, both of which have a lepton number of +1. So we've got 2 on the right hand side here, but only 0 on the left hand side. So they don't equal, so this isn't possible. This one here is possible because although strangeness isn't conserved, it doesn't have to be conserved in the weak interaction. So that was just a quick reminder, and there's a video series linked in the description if you're watching this and thinking, what is happening? A video series where all of this is explained. It takes about an hour and 50 minutes to watch through. And then you'll see how to lay out your answers and how to figure out if particle decays are possible. Well, that's what we're going to find out. So here are 5 particle decays. Some of them are possible. Some of them are not. All I want you to do is figure out, and I'll tell you, 2 of these are not possible. Which 2? And if you could write that into spiral, which 2 of these are not possible? A bonus points if you can tell me why. Unfortunately, I couldn't use the new symbol easily here, so I've just used a V. And down here it was worse than that. I couldn't use a subscript mu, so that just says a U, but that should be a mu there. Which 2 of these are not possible? Remember, baryon number has to be the same on both sides. Charge has to be the same on both sides. Electron lepton number has to be the same on both sides. Muon lepton number has to be the same on both sides. Strangeness doesn't. It does for the strong interaction. It doesn't for the weak interaction. Which 2 are not possible? So this is where knowing what particles are what becomes very, very helpful. Kaons, are they mesons or baryons? Sigma particles, mesons or baryons? This thing down here, a 𝗳 particle, meson or a baryon? What's its strangeness? Well, it doesn't really matter what its strangeness is, because strange doesn't have to be conserved. Anti-K0. It's a K0 with a bar over the top. What's that? Is that a meson or a baryon? Which 2 are not possible? If you can only figure out one of them, then tell me one of them, and we'll take it from there. Don't give up. Keep going, keep going, keep going. Okay, I'm going to hide the names and I'm going to show the answers that are coming through at the moment. I've hidden the names here, as you can see. Only a few answers. We've got sort of 2 still working out the others. We've got 1, 3. We've got 1, 2, maybe 5. So there's a lot of disagreement here so far. Wombat, you're spot on. Well done. Jack, you're spot on. That's correct. I marked 1 as correct, but the reason for number 3 is marked. 3 isn't because of strangeness. Strangeness doesn't have to be conserved. But your answer's correct. It's just the reason's not. Oh, I didn't even spot that. Yeah, you were correct. You got the right to, anyway. Yeah, well done, Wombat. Okay, let's give you a clue. The first one is not possible because we've got a meson on the left, so baryon number 0, but on the right we've got a baryon and 2 leptons. So the baryon number in total on the right would be 1. 1 doesn't equal 0, so it's not possible. I could make it work if instead of a proton I put a pion. That works. That's possible. So the mistake here was to put a baryon instead of a meson in. I'll do the next few. So the second one is possible, perfectly possible. The third one is not possible because I've got the wrong. I've got here lepton number that's not conserved. It's muon lepton number. You can't just have a lepton appearing on the right without an anti-lepton to cancel it, or a lepton on the left. Lepton number on the left is 0. Lepton number on the right was +1. That doesn't balance. So that's not possible. But we could make it work if instead of a neutrino we put a pion, for example. That's a possible decay. The fourth one's perfectly possible. No reason why not. This is a meson equals a meson plus a meson. We can do that. No reason why not. 0 charge equals minus charge plus positive charge. That works. And strangeness doesn't have to be conserved, and there's no leptons, so that works. And the last one's possible as well. Muon, muon, lepton, lepton. And the positron, this symbol here, has a lepton number of -1 because it's antimatter. And the neutrino has a lepton number of +1. So the lepton number on the right-hand side is a total of 0. On the left-hand side is 0, so that's possible. Okay, so 3 of these are not possible. Which 3? Right, so the word conserved there, Wombat, is a technical word. Conserved means that it will always be the same. You can have a weak interaction where strangeness just happens to be the same, but that doesn't mean that strangeness is conserved. So in the weak interaction, strangeness is not conserved. Could just happen to be the same, but it's not conserved. The strong interaction, strangeness is conserved. It's also conserved in the electromagnetic interaction. So what 3 of these are not possible? Correct answers are starting to come in. This is good. Okay, so answers are starting to come in. Yeah, the first one is that's not possible. That's not possible at all. Why is it not possible? Well, look at the charge. +1 does not equal -1 plus 0. So that's not possible. But if this was, instead of a delta minus, it was a proton, for example, that would be fine. Look at number 2. That's perfectly possible. Nothing wrong with that. We've lost strangeness, but we can do that. We're allowed to do that in the weak interaction. This is a matter lepton. This is an antimatter lepton. So they have a lepton number in total on the right-hand side of 0, which is the same as the lepton number on the left-hand side. And charge, +1, -1 on the right-hand side is 0. 0 on the left-hand side, that's fine. Then we've looked at number 3. Is number 3 possible? Well, no, because we've got a baryon appearing on the right-hand side. So baryon number isn't conserved. We've got a lepton, a muon. One more time, I will get it right. Too many words. A meson on the left-hand side, so baryon number is 0. But this is an antibaryon, so it has a baryon number of -1. These two are mesons, so baryon number of 0. So 0 does not equal -1. Baryon number is not conserved. But if that was a pion, for example, that would be fine. Third one, yeah, no problem. Fourth one, sorry, yeah, no problem, that's fine. We've lost strangeness, but we can do that. And the fifth one is not possible because charge isn't conserved. 0 on the left-hand side, but -1 on the right-hand side, you can't do that. But if, for example, this was a lambda particle, that would be fine. We can do that. Now, I've got loads of these. Absolutely loads of them. And so if you want, pause the video, pause it when you're watching this back later. You can pause it and then you can double check what's possible, what's not possible. I'm about to reveal the answers in 3, 2, 1. There we go. And then another one here. So what's possible, what's not possible. I'm about to reveal the answers in 3, 2, 1. And then I've got another one here. I've got loads. About to reveal the answers in 3, 2, 1. Oh, and one more. I was far too ambitious. I didn't know whether we were going to rattle through this very quickly or it was going to take a bit longer. I wasn't sure. 3, 2, 1. So you can watch those back later and find out what's possible and what's not possible. The third thing I wanted to look at is interaction diagrams. Yeah, exactly. So the third thing I wanted to look at is interaction diagrams. So here is a beta minus decay. Some particles are missing. 1, 2, 3, 4, 5 are missing. And this is a pretty typical multiple choice question. What's the particle that's missing? Or sketch a diagram. These used to be called Feynman diagrams, but in your A-level spec, they do them wrong. And the main difference between what you'll see here and an A-level, apart from the fact I used a dotted line because I didn't use a wiggly line because it wasn't easy to do on Excel. But the main difference here is this. The arrows here are going backwards for antimatter. And this was Feynman's interpretation of antimatter. I don't really have time to go through these. I'm really sorry. We were pushed. I tried to get too much done. I was too ambitious. But if you watch this back, I'm hoping you do still get something from it. So filling in the blanks for beta minus decay, we start with a neutron, which is going to turn into a proton in this decay. Why is it that antiparticles go back in time? Well, it's not necessarily the case that they do. It's just that's an interpretation. Yeah, that's an interpretation. It's because of this, Wombat. I'm going to show you something amazing. I'm going to go a little bit over the time that I usually use, but I'm going to show you something amazing with Feynman diagrams that you don't learn about in A-level, about why these are so powerful, or one of the reasons these are so powerful. So the neutron turns into a proton. That means there must be some negative charge being spat out in the process. That's a minus boson, W minus boson, which will then very quickly decay into matter and antimatter. The matter will be an electron because it's beta decay. That's where the negative charge has gone. So the antimatter has to be an antineutrino. Now you see this blue line going up there. traditionally you'll be taught that the vertical axis is time. In other words, the particle, the line representing the particle at an instant in time, I can't actually pause this line because I've animated it, but the line representing the particle at an instant in time here is moving to the right, and then here is moving to the left as these two particles move away. And that's the interpretation we use. And because charge is always conserved, charge is 0 here, has to be 0 here, has to be 0 here. And that's why it's plus charge and minus charge. And that's something you might learn about. If you follow it up, we've got the neutral charge, and then at all points along this line, we've still got neutral charge because -1 plus 1 is neutral. That's how you learn about these Feynman diagrams. But there's a more powerful thing you can do with them. So filling in the gaps for electron capture, a proton in a particularly proton-rich nucleus can absorb one of the electrons from the inner orbital. And it does that by way of a W boson. Now, here I've got a W plus boson. I could very equally have done it the other way around with a W minus boson. For some reason, A-level specs call that electron-proton collision instead of electron capture, but this is what we've got here. And then we've got particle 4 here. The proton giving out its positive charge becomes a neutron, and the electron losing its negative charge when it comes into contact with this W plus boson becomes a neutrino. And so we've got the same idea. Along this blue line, which represents an instant in time, we have exactly the same charge at all times. It's conserved. Plus and minus, then still plus and minus, which equals 0, and then it's still 0. So that's something that you'll learn about. And we've got beta plus decay, which is now it's the opposite way around. A proton in a proton-rich nucleus, instead of absorbing an electron from the inner shell, which is what you might get for electron capture, it will decay into a neutron by emitting a W plus boson, which will decay into a positron and a neutrino. And we could do the same thing with a blue line, looking at the charge at an instant in time, and we can see that it would all still balance. And there's plenty of examples. This is the example I mentioned before, where some reason A-level separates electron capture and electron-proton collision for some reason. Actually, both of these would happen, and there's a probability of both happening, and you wouldn't be able to tell which one happens. They both happen simultaneously. But I wanted to show you some of the weird tricks with, I just need to get through this, some of the weird tricks with Feynman diagrams. So neutron, neutrino collision, neutrino collides with a neutron. How does it do that? Well, we're going to have to emit a particle. Neutrino is matter, so we have to have matter here as well. Neutrino can turn into an electron, which means this has to have positive charge because this branch is going to have negative charge, and that way everything works out. But this is the one I wanted to spend a bit more time focusing on. You could do this with all of them, but I just picked this one, the last Feynman diagram we're going to look at, and why Feynman diagrams are so magical. We fill in the blanks like this. Remember, the arrows show you whether it's matter or antimatter. So a backward arrow here is antimatter. A backward arrow is antimatter. So here's my picture of a proton colliding with an antineutrino. This antineutrino is moving towards the proton. Don't be confused by the direction of the arrow. That just means it's going backwards in time. And so we have our time axis like this. An instant in time, we can see charge is conserved at all points. We can see that baryon number is conserved. If I coloured in baryon number, this would be +1, +1, +1, +1, +1, +1, +1, and everything over here is 0. If we looked at lepton number, it's lepton number over here of -1, -1, -1, -1, -1, -1, -1, -1, all the way along, and everywhere else is 0. So all the numbers are conserved on this Feynman diagram when I move the axis of time vertically, when I look along time. But what happens if I choose to look at an interaction where time is running sideways? I don't mean time is running sideways. What I mean is instead of a proton and a antineutrino colliding, I have a neutron and a proton colliding. Well, I can't quite do that, but neutrons, when I move the axis now, look, I haven't changed the arrows. The arrows are still all in exactly the same direction. So now it's not a neutron, it's an antineutron. I've changed this vertex here, so it's a proton antineutron, and it still works. This is no longer an antineutrino, because now the arrow's pointing in the same direction as the axis of time, so now it's a neutrino. That's still a positron. The arrows are all in the same direction. The flavour of the arrows is still right. This is still a proton-like thing. This thing here is a neutron-like thing. It just happens to be antimatter. This thing here is a neutrino-like thing, and this thing here is a electron-y, positron-y-like thing. It's just... And I haven't moved the arrows at all. But it still works. It's even weirder than that, because I keep the arrows exactly the same way, and now I look at everything going backwards in time. I've still got a proton-like thing, a neutron-like thing, an electron-like thing, and a neutrino-like thing in this interaction, and it still works. Okay, now the arrow is pointing in the same direction as the axis of time, so this isn't a positron anymore, it's an electron. But now this isn't a proton anymore, it's an antiproton, that's an antineutron, that's a neutrino, but it all still works. Okay, because we're going backwards in time, well, the charge is now reversed as well. But the quantum numbers still balance. That's the power. I mean, Wombat, you've said neat. When I first found out about the power of Feynman diagrams, when a teacher I was observing a teacher teaching Feynman diagrams where the arrows represented the direction particles were moving, so they weren't Feynman diagrams, and they said, and time has to go in this direction on this particular diagram. I thought, no, you're missing the point. You're missing the point. The universe doesn't care what direction time runs. That was Feynman's revelation. It doesn't matter what direction time runs. Particle physics works either way. Wow! Time independence. I could have talked in this session for about 4 or 5 hours. And, you know, when I teach, I'd spend far too long on topics like this because they are exciting topics. And if you're a GCSE student who's absolutely baffled by some of the things we were doing earlier, watch it back, watch that video series, see what you think. This is early A-level stuff. It's the new stuff. It's the stuff that's good fun. If you're thinking, I'm just not interested, then, well, I mean, you can always do A-level chemistry and maths, I suppose. But for me, I don't know how you can live in a universe with all this and not be absolutely fascinated. And that's all we have time for. Well, thank you very much. I know it's a Sunday. I went on too long. I didn't get a chance to do everything I wanted to do. I still hope it's been useful. If nothing else, it's given you a flavour of particle physics. And you can see that there really isn't that much. It is really fun. It is, Freya. And it gets even better when your mathematical skills, when you can handle matrices and you learn the matrix notation for the Schrödinger equation, Dirac notation. Oh, it opens up this whole new world of physics for you. So if nothing else, if you're watching this as a GCSE student or an AS level student, you're thinking, this is just too much. I can't learn this. I'm hoping you've seen that actually it's not that much to learn. And everything just clicks together. Thanks, Tilly. Yeah. Everything just clicks together. And it's so, what's the word I'm looking for? Satisfying when everything just works together. Because if you don't see this before you see the quantum physics stuff, the quantum physics stuff can be absolutely, it just seems like nonsense. So this helps you get some grounding of why it all works. Now, next session is on quantum physics, but it's only going to be some of the basics, he says, tongue-in-cheek, because there's nothing basic about quantum physics. We're going to be looking at it, again, AS level. It's accessible to GCSE, but it's going to be it is going to be challenging. But if you're a GCSE student, come along because it gives you a taste of A-level. I've tended in the past to focus on GCSE all the way through series 1 and 2 of what I'm doing. I focused very much on GCSE, so I'm trying to balance that a bit and put a bit more A-level into these sessions. And let me know, give me some feedback. Leave some comments below or drop a message to me on Facebook or something. Let me know if you're finding this useful or if you're saying, do you know what, the A-level stuff is fine, but it's too much for me. Can we just do some GCSE revision? It's up to you. I'm here to help you. Thank you very much. I'm impressed. You all made it. Go enjoy the snow. Be safe. get exercise in the snow, sorry. Sorry, I've just seen a message from Lex. Will we ever go over Feynman diagrams at any point in the quantum stuff? Not really, no. We're going to be focused on algebra more than anything with that. And will there be a video series for quantum physics? I can make one, Ted. At the moment, I'm doing one for calculus from a physicist's perspective. When I first learned calculus at A-level physics, so try again. When I first learned calculus and A-level mathematics, it didn't make any sense to me. I did not do well in A-level mathematics. Now, I wonder whether anyone else is in a similar situation to me. When I went to university and started learning calculus from physicists, it just made perfect sense. I don't know what it is that made it make sense when a physicist taught it. Now, different people teach it in different ways. So I'm going to teach calculus. Do we learn about the zeta function? Maybe. Rich, I don't actually know what the zeta function is, so maybe. But I won't be teaching it. Yeah, it could be useful, Wombat. The thing is, it might not be. It's a bit of a risk because I'm not a maths teacher, so it might actually do more damage than good. But we'll try it. We'll see how it goes. And if you like it, let me know. Give me some feedback. Anyway, I've spoken enough. Everyone, take care of yourselves, and I will see you next week. Thank you.